All right, well, welcome back everyone. We're going to continue our discussion of kinetics here today. So I kind of broke the kinetics chapter into two different parts. The first part was really looking at rate and determining rate law. So the primary focus there was those problems where you've got a set of experiments and you're using how the rate related to the changes in concentration to figure out what the rate law of the reaction is. The second part here is what are called integrated rate laws, where we want to kind of specifically evaluate the relationship between concentration of reactants in our reaction mixture and time. And in order to do that, we use what is called an integrated rate law. So we're actually taking the rate law we talked about last time and we're integrating that equation with respect to time from the initial concentration to a concentration at a certain time. And we get a set of equations that we can do some useful problem solving with. So if we start here thinking about a first order reaction, for a first order reaction, we know that rate would be equal to the rate constant times the concentration of the reactant, and the exponent there would be 1, which we usually wouldn't have to write the 1 since it doesn't change the value. That would be a first order reaction because there's a single order dependence on the concentration of R. Well, if we take this reaction and we do that integration, and again, this is an introductory chemistry class, you don't need to have had calculus here, so we're certainly not going to hold anyone to integrating equations. But if we do integrate this equation, we get an equation that looks like this. We have the natural log of the concentration of our reactant at a specific time, time t, minus the natural log of our concentration at time 0, so when the reaction started, is equal to minus k reaction constant and times t, the specific time. So this time matches this concentration. Whatever time we would plug in here would correspond to what's the concentration of our reactant. Now, once you have this equation, you've done more than half the problem because everything else is just plugging into this equation to solve for whatever's missing, which is what we'll do in the example right here. But before we do that, there's another version of this equation that can be useful as well. And I'm going to put or there because it's the same equation, it's just rearranged. And because of the logs, rearranging the equation is maybe a little more complicated than you might expect. Depending on what you remember about logarithms. So if we take the natural log of the ratio of the concentration at time t to the concentration at time 0, that is also equal to minus kt. So because of the way logarithms work, subtracting here, dividing here gives you the same answer. So what I'd want you to think about is what information is provided in the problem. If you are solving for a concentration, either concentration at time t, or for some reason you're trying to figure out what the initial concentration was, you probably want this equation. You'll be able to plug in the one concentration you know, take its log, becomes a numerical factor. If you're looking for a ratio of concentrations, like percentages, right? How much time does it take for there to only be 30% of the sample left? You want to use this version of the equation because these are already ratioed the same way they would be in a concentration. So now this can become one variable. If you mix which one goes with which equation, it is pretty common for people to end up with answers that aren't correct because of the way logarithms work a little bit differently than kind of standard math. So pick the right equation to start with and it'll help your problem work a little bit easier. The other thing that I specifically want to mention here, I said once you get this equation, you've done a good chunk of the work you need to do for each problem. So sometimes the key to the problem is figuring out which equation is the right one to use. And we mentioned this last time, but K can have different units. The rate constant can have different units depending on the order of the reaction. So it's worth thinking about the units a little bit here for K and how those units tell us whether we're looking at a first order, second order, or other ordered reaction. So we know that rate is molarity per second. So the left side of that equation is molarity per second. we know the concentration here is molarity. So I've got molarity on this side and on this side. K is in here to help numerically, but also to help balance out the units. So the units on K here would have to be 1 over whatever time unit we're using, right? Generally it's seconds, but it's not always seconds. In fact, it's hours here in the example that I'm looking at, but 1 over the time unit. So first order reaction, the units for K are 1 over time or reciprocal time units. Sometimes the problem won't tell you it's a first order reaction, but if it gives you K, it kind of is telling you just sort of in this chemistry code that we might use. Okay, let's look at the sample problem here. And again, once we have the equation, it's kind of just plugging in and doing some math. So sucrose, sugar, decomposes in acid solution to give glucose and fructose. Now, by definition, a decomposition reaction is we have one molecular species breaking apart into more than one. So if there's only one reactant, those are almost always going to be decomposition reactions, and that means they are going to be first order because you just have that one reactant that's breaking apart. Now we're told here the reaction is first order in sucrose, and that's fine, but if that part of the sentence was missing, we could still figure that out from the units here, like I just explained. Rate constant at 25 Celsius is 2.1 per hour or reciprocal hour. That's consistent with first order reaction rate constant. Okay, we're given the initial concentration of sucrose, 0.010 moles per liter or molarity. We want to figure out the concentration after 5 hours. So we've got K, we've got the time, we've got the initial concentration. The only thing missing is the concentration at time t. So we want this first version of the equation we talked about. Natural log of the concentration at time t, which is 5 hours, minus the natural log of the initial concentration at time 0, equals minus kT. So I'm going to use x here just to make writing a little easier for what we're trying to solve for, the concentration at that time. And I'm just going to plug in the other variables. The initial concentration, 0.010, so I'll need to take the natural log of that. On the right side, I've got that negative sign. My rate constant here is 2.1 per hour, and the time is 5 hours. Now, those units match up, hours and per hour. Be careful of that. It's a sort of sneaky trick you can throw in there just to make it a little more complicated, is to make sure those units don't quite match up. Okay, doing some math here. Natural log of x. If I take the natural log of 0.01, that is minus 4.605. So watch your negative signs there. Two negative signs are going to turn into a positive. And then on the right side, 2.1 times 5. And this side of the equation will be negative 10.5. Now, two negatives there, that's really a positive. So that would be the natural log of x plus 4.605 equals minus 10.5. From there, I need to subtract 4.605 from each side so that I get natural log of x on one side, and that would give me minus 15.105 on the other side. Now, to isolate x, what we're trying to solve for, we need to get rid of the natural log. So if you look on your calculator, the second function of the natural log on every calculator I've ever seen that has those two keys is the reciprocal of the natural log, which is taking the exponential function, lowercase e, and raising it to the x power. So I can get x on this side if I take this side and I raise whatever value is on this e to whatever value is on this side. So e to the minus 15.105 will give me x. So plugging that in, x, which again is the concentration of the reactant at time t, would be, so second function there for e, minus 15.105. And we're kind of limited to 2 sig figs here, so I'll round this answer to 2.8 times 10 to the minus 7th. Now this is concentration, so this would be molarity, right? And that would be my answer. That's my concentration at 5 hours. Now, a useful thing you can do here, knowing how this reaction is working, we know that after a certain amount of time, the concentration should have gone down. It's worthwhile to compare this value to this value and make sure what you got is a lower value. If you started at 0.01, your concentration cannot get higher in your reactant. It must be getting lower. That's the case here, right? You can at least check that you didn't make some kind of catastrophic math mistake there.